Deep in the heart of the Tsugaru Strait between Honshu and Hokkaido in Japan, the open Pacific Ocean forces through a channel 23 kilometers wide, where winter storms reach 40 meters per second, and the seafloor sits 140 meters below the surface. For a century, the only crossing was a ferry. In September 1954, a typhoon sank 5 ferries simultaneously. Over 1,400 people drowned in the water of this strait. 3 weeks later, the Japanese government approved a study for a fixed tunnel crossing. A beautiful nightmare for geotechnical engineers. The challenge bore 54 kilometers through rock below the seabed, in rock formations that only the boring machines will fully characterize once they are inside it, at depths where the water pressure on every crack in the lining would drive water through it at fatal force. This is the Seikan Tunnel under the Tsugaru Strait, the longest undersea railway tunnel ever built. In 1964, the pilot tunnel boring began. Survey drilling from the surface had mapped the rock along the proposed alignment. What the cores showed at the critical depth range is the event the whole program is building toward. A fault system runs diagonally across the alignment, and the rock on both sides of the fault is permeable. Groundwater in those permeable zones is under the full pressure of 140 meters of ocean above it. What happens when the pilot heading enters the fault crossing will determine whether the main tunnel program can continue. Over 200 machines were deployed at the 2 portal sites. An army of 3,000 workers arrived. The pilot heading entered the rock from the Honshu side on a March morning. The pilot tunnel will reach the fault zone long before the main bore. It will be the first machine through. We go small first. The pilot tunnel is a probe bored far ahead of the main excavation to drain groundwater from the rock before the main bore reaches it. The pilot heading runs at a lower elevation than the planned railway floor. Water that enters the pilot heading drains away from the main works above it by gravity. We will know the full character of every ground condition ahead of the main tunnel because the pilot heading has already passed through it. The pilot heading enters rock conditions that no surface survey can fully predict. That is its purpose. The drill and blast cycle advances the pilot heading through competent rock at 6 to 8 meters per day. Blast holes are drilled into the face in a pattern calibrated to the rock strength. The charges fire the rock fragments. Mucking machines load the broken material onto narrow gauge rail cars. The cars haul back to the portal. Fresh cars go in for the next cycle. The haul distance grows as the pilot heading advances. The rail network inside the tunnel extends with it. The main tunnel excavation follows the pilot heading by years, using the drainage and investigation data the pilot provides. The main bore is 8 meters wide and approximately 8 meters tall. Steel arch ribs install immediately after each blast cycle. Lagging boards cover the full arch between the ribs until the concrete lining is cast behind the advancing face. The lining concreting uses a traveling formwork that advances in stages. Pour, cure, advance. The fault zone crossing is the event the whole program has pointed toward since the surveys first identified it. The pilot heading reaches the fault, and water enters through the first fault intersection under pressure. The inflow blows out the grouting equipment being used to seal the rock ahead. Probe holes push forward from the face into the fault material. The readings confirm the fault extends at least 40 meters further along the alignment. We cannot advance at the normal rate. Grouting crews work in a protective cavity cut ahead of the face. Cement is injected into the rock under increasing pressure over 6 weeks until the inflow rate drops to manageable levels. The pilot heading resumes advance. The fault zone is crossed. The main bore follows the same grouted path years later. Cheering. The Seikan Tunnel opened for rail operations in March 1988. The construction army packed their equipment from the 2 portal sites over 4 months. The narrow gauge haulage rail inside the tunnel was removed and replaced with standard gauge track. Ventilation installations were completed and tested. Safety refuges in the tunnel walls were fitted out and equipped. The first passenger train entered the Honshu portal in the morning and emerged at the Hokkaido portal 54 kilometers later, 23 minutes after entering the tunnel. The ferry crossing that had taken 3.5 hours in good weather and been cancelled entirely, in bad weather was replaced by a 23-minute journey that runs regardless of what the strait does on the surface above. 23 minutes. The trains that use the Seikan Tunnel today pass through a section of tunnel that sits 100 meters below the seafloor, making the deepest railway passage under the ocean anywhere on Earth. Passengers look out the window and see only the concrete lining passing in the tunnel lights. Below them, the ocean does not know they're there. A testament to what engineers build when a storm drowns over 1,000 people and a country decides that the crossing must be made safe. Where the ocean once owned the strait, now a railway runs beneath it. Japan built it because the storm that killed those passengers in 1954 was the last time the crossing was left to the weather. An engineering marvel under the Tsugaru Strait. If projects like this move you, subscribe so you never miss the next one. Drop a comment and tell us where in the world you're watching from. The refuge chambers cut into the Seikan tunnel walls at 2-kilometer intervals provide shelter for passengers and crew in the event of a fire or emergency inside the tunnel. Each chamber holds air supply, communications to the Surface Control Center, food and water supplies, and first aid equipment. The blast-resistant doors seal the chamber from the main tunnel in the event of fire. The chambers are inspected on every maintenance round. The supplies rotate before expiry. The doors cycle through their full movement range on the inspection schedule. The chambers are ready for an event that has not yet occurred. The drainage system inside the tunnel collects groundwater that continues to enter the lining through minor cracks and through the drainage layers behind the lining. This water flows to sump chambers at the low points of the tunnel alignment. Pump stations in the sump chambers lift the collected water to rising mains that carry it to the surface. The pump stations have duty and standby pumps at each sump. If the duty pump fails, the standby pump starts automatically. The standby pump capacity is sufficient to handle the full inflow rate without the duty pump running. The drainage system removes water from the tunnel continuously. The track in the Seacon Tunnel rests on a ballasted formation in the sections away from the portal areas, and on concrete slab track in the sections with the highest drainage and maintenance requirements. The ballast settlement rate in the main tunnel sections is lower than in surface railway tracks because the temperature and humidity inside the tunnel are stable year-round. Ballast that settles on a surface railway due to frost heave and thermal cycling does not experience those forces underground. Track geometry surveys run through the tunnel on a 6-month schedule to detect and correct any settlement that does occur. The Shinkansen high-speed service that now uses the Seacon Tunnel required modifications to the track geometry, the overhead catenary system, and the signal equipment throughout the tunnel length. The modification works took place during the nighttime maintenance windows between the end of the last evening service and the start of the first morning service. Engineers worked in the tunnel through the night, replacing equipment and adjusting alignments, and cleared the tunnel before the morning service began. The modifications extended the useful life of the tunnel infrastructure and increased the transit speed for passengers using the route. The construction of the Seacon Tunnel established techniques for driving long undersea railway tunnels that were applied directly to subsequent projects in Japan and that influenced the design and construction of undersea tunnels in Europe, Asia, and around the world. The methods developed for grouting the fault zone under the Tsugaru Strait became the standard approach for dealing with water-bearing fault crossings and undersea tunnel drives. The pilot tunnel advance strategy used to investigate ground conditions ahead of the main bore is now standard practice in tunneling through unknown geology under water bodies. The engineering knowledge embedded in the Seacon Tunnel program spread outward from the Tsugaru Strait to every deep undersea tunnel that followed it. The Seacon Tunnel is classified as a critical transportation artery by the Japanese National Railway Authority. Emergency response plans cover every scenario from derailment and fire to structural emergency and medical incident. The response plans assign specific responsibilities to railway staff, tunnel maintenance personnel, fire services, police, and medical services. Exercise drills run twice per year to test the coordination between all response agencies. The exercises include scenarios that involve the refuge chambers, the evacuation procedures, the surface access points, and the communication systems. The exercise findings are reviewed and the procedures are updated based on what the drills reveal. The tunnel lighting system uses LED fixtures mounted to the concrete lining at regular intervals along the full length of both running tunnels and the service tunnel. The LED fixtures replace the original sodium vapor lighting during a scheduled maintenance program. The LED system consumes significantly less electricity than the sodium system and produces a more uniform light level across the tunnel cross-section. The light level in the running tunnels meets the standard required for driver visibility in the ventilated section and for emergency visibility in a power failure condition. The emergency lighting circuits use battery backup units that maintain minimum light levels for the duration required by the emergency procedures. The Seacon Tunnel operation generates data that contributes to the Japanese Railway Authority's National Infrastructure Maintenance Database, track geometry surveys, lining condition records, drainage system performance data, and structural monitoring results are collected and archived in a standardized format that allows comparison with equivalent data from other railway tunnels in the national network. The database is used to predict maintenance requirements and to schedule capital renewal works before components reach the end of their service life. The predictive maintenance approach prevents emergency failures and allows maintenance budgets to be planned on a rolling 5-year horizon rather than responding to failures as they occur. The Seacon Tunnel established that a railway tunnel of 54 kilometers under an active sea strait is a feasible engineering project, with the tunnel boring and ground treatment technology available in the second half of the 20th century. This demonstration removed the technical barrier to undersea railway tunnel projects of similar scale elsewhere in the world. Projects that followed, including the Channel Tunnel between England and France, the Fehmarn Belt Tunnel between Denmark and Germany, and several undersea tunnels in Scandinavia, benefited from the knowledge developed during the Seacon program. The engineering information from the Seacon Tunnel crossed national boundaries and contributed to projects that served different populations in different parts of the world. The trains that cross under the Tsugaru Strait today carry passengers who were not born when the tunnel opened. For these passengers, the tunnel is the ordinary way to cross the strait. The alternative, a ferry that was cancelled in bad weather and took hours in good weather, is historical information. The crossing that cost over 1,400 lives in one night in 1954 and that the engineers spent 30 years making safe is now a 23-minute train journey. The engineers who built it are gone. The tunnel they built runs every day. The strait above it moves as it has always moved. The trains below it cross as they now always will. The service life of the Seacon Tunnel is projected to exceed 100 years from the date of opening based on the current condition of the concrete lining, the drainage systems, and the structural components. The projection is based on the measured rate of deterioration in the tunnel components since opening and on the maintenance program that slows that rate. The lining concrete shows surface carbonation depth consistent with the long-term exposure to tunnel atmosphere. The carbonation depth is within the range that the design cover to reinforcement can accommodate before the steel is at risk of corrosion. The design cover was specified with the 100-year service life in mind. The concrete placed in the 1970s and 1980s is performing as the specification required. The Seacon Tunnel is a physical object made of concrete, steel, and grouted rock. It has no awareness of the storms above it, the ships crossing the straight's surface, or the passengers in the train cars that transit it twice an hour. It absorbs the groundwater that continues to enter through minor cracks in the lining and sends it to the pump sumps where the drainage system removes it. It carries the train loads on the track that rests on its invert slab and transfers those loads to the surrounding rock through the lining. It maintains the tunnel geometry that the engineers designed into it 40 years ago. It does its work without variation. The Tsugaru Strait runs above it. The trains run through it. The rock holds both. The Seacon Tunnel is 54 kilometers long. 23 of those kilometers are under the sea. The deepest point is 100 meters below the seafloor. The strait above is the most dangerous water in Japan. The trains below cross it every 23 minutes. The ferry that the tunnel replaced was cancelled for weather 30 days per year. The tunnel has never been cancelled for weather. The rock between the train and the ocean does not change. The Seacon Tunnel is not the most famous undersea tunnel in the world. The Channel Tunnel between England and France holds that distinction, but the Seacon Tunnel is the deepest, the one built in the most difficult conditions, and the one whose construction established the methods that every subsequent undersea tunnel has used. It was built without the computational tools, the precision monitoring systems, and the advanced boring equipment that later projects had available. It was built by 3,000 workers over 24 years using the best methods available at each stage of its construction. It opened. It works. It has worked every day since. The strait above it is the same strait. The tunnel below it is the same tunnel.